Good day, everyone. Today, our topic is about differentiating a definite integral. And we recall that differentiation is the process of finding the derivative. So this time, we are going to find the derivative, or we are going to differentiate a definite integral. Then I will be presenting to you two ways on how to find the derivative or on how to differentiate a definite integral. So keep on watching.
So here, differentiating a definite integral, we'll be using the second fundamental theorem of calculus. So it says here that if f is a continuous on a closed interval a and b, and x which is any point on the closed interval a and b, then this equation holds. This means that the derivative of the function big F, where big F is the antiderivative, is given by this. So this is equal to the derivative of the definite integral. Okay? This is integral of f of t dt, where t is the variable of integration evaluated from a to x. Then we expect that after evaluating the definite integral, this becomes a function of x, right? So after that, that's the time we are going to find the derivative of that function with respect to x. And that is equal to the small f, this one, f of x. So, as an example, if we are asked to find the derivative of the definite integral, let's say integral of t squared dt, evaluated from 1 to x. So first, we are going to get the definite integral first. Okay? So, and evaluating the definite integral, we have to get the antiderivative first. The antiderivative of t squared dt is t cubed over 3. Okay, then evaluate that one from 1 to x. Using the first fundamental theorem of calculus, we just simply substitute x to the variable t. So this becomes x cubed over 3 minus 1 raised to 3 over 3. Okay? So notice that this is now a function of x. So that's the time we're going to get the derivative of this function with respect to x, and we use this notation. Now, how to get the derivative? Using the differentiation rule, we just simply use the power rule. So the derivative of x cubed raised to 3, 3 will be multiplied here. So this becomes 3x and 3 minus 1. So this becomes 3x squared over 3. So 3 will be cancelled. So we have what? We have x squared. X squared only because the derivative of 1/3, since 1/3 is constant, so this will be 0. So the answer is x squared. Next is the derivative of the definite integral t squared dt evaluated from 1 to 4x. Okay, first, again, we are going to get the derivative, definite integral first. What is the antiderivative? The antiderivative is t cubed over 3. Then evaluate that one from 1 to 4x and use the fundamental theorem of calculus. We just simply substitute 4x to the variable t. Then this becomes quantity 4x raised to 3 over 3 minus 1 raised to 3 over 3. Right? So since 4 is raised by 3, so we have to multiply for 3 times. So this is equal to 4 times 4 times 4, or 4 cubed, is equal to 64x cubed. So this one is equal to 64x cubed over 3 minus 1 over 3. Then get the derivative with respect to x. Now, we just simply multiply the exponent 3 to 64, and this is equal to 192 x squared over 3. Now, 192 x squared over 3 is just equal to 64 x squared, because the derivative of 1/3 is constant. This 1/3, I mean, is constant, so the derivative is 0. So the answer is 64x squared. Okay, so the next example, the derivative of the definite integral t squared dt evaluated from 1 to x squared. We have to get the definite integral. So what is the antiderivative of t squared dt? This is equal to t cubed over 3 evaluated from 1 to x squared. So we just simply substitute x squared to the variable t. So this becomes quantity x squared raised to 3, right? Over 3 minus 1/3. And we all know that x squared raised to 3 is equal to what? X raised to 6 over 3 minus 1/3. Then get the derivative of this function. So we just simply multiply 6 to here. So this becomes 6x raised to 5, and 6 divided by 3 is 2. So we have what? 2x raised to 5. Okay, so this is how we do, or this is how we apply the fundamental or the second fundamental theorem of calculus. Notice that the resulting function, this is what we are referring to our small f. Okay, this is our small f, x squared, 64x squared, and 2x raised to 5. Okay, so in the next slide, I will be presenting to you another way. Here is another way. For example, okay, so we are going to find the derivative of this definite integral. In the previous slide, we just simply find the definite integral. Then after finding the definite integral evaluated from 1 to x, then we get the derivative, right? But this time, we just simply substitute, okay? We just simply substitute the upper limit to the variable in the integrand, okay? And we multiply that one to the derivative of the upper limit minus, we simply substitute the lower limit to the variable in the integrand times the derivative of the lower limit, which is 0. To understand, so since the upper limit is equal to x, right? So all we have to do is just to substitute x to the variable t. So this becomes x raised to 2. And as I've said, that we have to multiply this one by the derivative of the upper limit because we are using the upper limit. What's the derivative? It's 1. And we just simply minus, because in the fundamental theorem of calculus, we just simply use the subtraction process, right? So minus, we simply substitute 1 to the variable t. So supposed to be there is 1 squared and times the derivative of 1, which is 0. So this one here, this supposed to be there is minus 0 here. But since minus 0 is just equal to 0, so this is the final answer. We have x squared. Okay, so what have you noticed? The answer is just simply equal to what? Is just equal to the small f. And we just simply substitute the upper limit to the variable in the integrand. So this is a kind of a shortcut or shorter method compared to the method that we were using a while ago. Okay, so next example. Okay, how can we do this? So again, using the shortcut way, we just simply substitute this upper limit to the variable in the integrand. So we expect that this is equal to what? 4x, quantity 4x raised to 2, and times the derivative of 4x. What is the derivative of 4x? Is 4. Supposed to be there is 1. There is minus, substitute 1 to the variable in the integrand. So 1 squared And since the derivative of 1 is 0, so that's why we just only copy this side. So quantity 4x raised to 2, this is equal to what? 4 raised to 2 is 16. So we have 16x squared times 4, which is 64x squared. Okay, so recall we have the same answer with the previous example that we have. Next example, the derivative of the indefinite integral of t squared dt. Again, we just copy this one, then or we just substitute this one to the variable t. So we have a quantity x squared raised to 2 and the derivative of x squared, which is 2x. Okay, so this is equal to x raised to 4. Okay, x raised to 4 times 2x is equal to 2x raised to 5. So this is easier compared to the long method that we were using a while ago. Next, the derivative of the definite integral. So simply substitute again x squared to the variable t and find the derivative of x squared. What is the derivative of x squared? 2x. So we have sine of quantity x squared times the derivative, which is 2x. Next, the derivative of the definite integral of tangent t dt. Okay, so we just simply substitute x squared plus x to the variable t and find the derivative of this. You multiply to that. You multiply that one to the answer after substituting this upper limit to the variable t. So we have substitute again tangent. You substitute the upper limit x squared plus 2 times the derivative of x squared plus 2, which is 2x plus 1. Supposed to be there is minus. You substitute 1 to this variable t. Sorry. So um, we have an answer here which is not equal to which is a constant. But since we are going to multiply that one to the derivative of 1, which is 0, so that's why we have minus 0, and the answer is this one. Okay, so next is the derivative of the definite integral t squared dt. Again, using the shorter way, we just simply substitute to the variable t. So we have sine squared x. Okay, then the derivative of sine x is cosine x, so this will be multiplied here. Then minus what? We just simply substitute tangent x to the variable t, so we have minus tangent squared x and times the derivative of tangent x, which is secant squared x. Okay, so this is how we differentiate definite integral using the second fundamental theorem of calculus. Okay, so thank you so much. Hope you like this video. And don't forget to share the learning that you've got from this video. Thank you once again and God bless.